to fast-track complete beginners with no prior knowledge of building a hobby-grade drone. The tools you need for the build are pretty basic, however the course does assume that you know how to use a soldering iron and possess some basic electronics knowledge. I will go over each component needed to build a drone, followed by a build video showing you a drone being assembled step by step. How long the course takes a drone. We will start by exploring the foundation of any DIY drone, the frame. It's important to choose the right frame since usually it will influence the rest of the components. So choosing things such as your motors, speed controllers, or even flight batteries will be dependent on the frame. The type of drone you want to build will also influence the type and the size of the frame. Let's say you want to build something small and fast to race around while wearing FPV goggles to get that pilot seat experience. Or maybe you want to build a large flying machine capable of lifting heavy cameras. Whichever type of drone you're after, one thing is certain, having the right frame does make a difference. Now do remember that if you don't understand any of the jargon talked about, you can always refer back to the jargon buster in the previous section. Right, what is the big deal with frames anyways? Why do some of the high-end frames cost a small fortune, whereas others only cost a fraction of it? In the world of DIY drones, frames are sometimes overlooked. However, they do a lot more than just keeping things together. In fact, the design and the material the frame is made from affect the flight characteristics of the drone quite a bit. Sometimes, badly designed frames can introduce unnecessary vibrations or affect the center of gravity of the craft, which in turn make the flight controller on board work extra hard trying to keep everything stable. So, let's have a look at what makes up the frame. Frames can come in all types of shapes and configurations, and can have a varying degree of assembly required. Sometimes they come as a single piece where all the components are mounted onto, and other times you need to put a few things together. But the main distinguishing bits on a frame are usually the base and the arms. Let's have a look at what they do. The base, it's responsible for housing most of the important components, so things such as the flight controller, the radio receiver, and even cameras if you have any. Quick tip, to optimize how the drone flies, we have to think about where everything goes. Let's take the flight controller for example. It uses highly sensitive motion sensors to control the flight, and most of them will be programmed with the assumption that it will be mounted centrally on the frame. Another common thing that is mounted centrally on the frame is the flight battery. This is to keep the overall system balanced. And of course, a balanced system is usually a stable system. Next up, we have the arms, which will hold the motors and sometimes also the speed controllers. However, there is another important role they play in the background, which is that they minimize unwanted vibrations coming from the motors. Vibrations during flight can cause trouble for the flight controller with its sensitive motion sensors that usually keep things stable. If the vibrations are bad enough, it may even cause the drone to become unstable and crash. Now, another excellent reason to minimize vibration during flight is in the case of an onboard camera for video recording or even FPV flight. Outside of certain horror films, shaky footage is never really fun to watch. Okay, so what do we need to consider when picking a frame for our build? There are 3 things to think about. Arguably, the size of the frame will be the most important factor to consider, since it will depend on what type of drone you're building. For example, if you're thinking of fun flying and racing, then frames smaller than 300mm will be a good choice, since in this case agility and speed is the goal. Alternatively, say you wanted to build a drone specifically to do aerial shots, in which case frame sizes of 380mm and above would be a better choice. Generally speaking, bigger drones are better for video equipment in terms of lift capacity and stability. Quick tip, in case you're wondering about how the frame sizes are measured, the measurements come from measuring motor to motor through the middle of the frame. So, for example, top right motor to the bottom left motor. Next thing to think about is the material. The material your drone frame is made from needs to have the right balance between strength and weight. Ideally, we want the frame to be made from material that is lightweight, since lightweight frames will have a smaller impact to the overall weight of the drone, which in turn of course will give you a bit more flying time. On the other hand, it's also important to have a frame that's made from strong materials to prevent damage to the components during a crash. Which brings us to carbon fiber. carbon fiber based frames are pretty strong, relatively lightweight, and can survive most crashes. Price ranges from pretty cheap to sometimes pretty crazy money. Another common material for frames is glass fiber. They can be a lot cheaper compared to carbon fiber frames, which makes them great for budget builds. However, the trade-off in this case is that they are slightly less crash resistant. Now, on to the frame that we'll be using for the build in this course. This frame is quite easy to assemble and doesn't contain many parts. In this case, the base and the arms are all part of one single thick carbon fiber plate, which of course can be both good and bad. During a particularly nasty crash, you will have to replace the entire frame, but on the flip side, there is a considerable reduction in weight, since there are no bolts and nuts mounting the arms. It is also a relatively small frame, only 210mm across. However, when paired up with powerful motors, it will result in a compact but powerful flying machine. To summarize, frames are specific to the type of drone you're building. A small frame is usually used when speed and agility is the goal. Bigger frames are useful for, say, aerial photography platforms. Carbon fiber is the preferred choice of frames, but it can be expensive. Whereas glass fiber is cheaper but can also be less crash resistant. In this course, we're building a 210mm Racer class drone, which will be powerful, agile, and a lot of fun to fly. This concludes the lesson about frames. Next, we'll learn about the muscles of the drone, or otherwise usually referred to as the motors. Hi everyone, welcome back. In this section, we'll have a look at how a drone works at the most basic level, followed by an overview of some of the design variations out there. If you want to jump straight into the juicy bits, you can skip ahead to the next section where we dive right into the understanding all the components and building the drone. Okay, so the term drone is not really all that descriptive. Technically, anything remotely controlled or pilotless can be called a drone. Even MIL-Bs are classified as drones. When we talk about drones in this course, we are talking about multirotors or multicopters. And to qualify as a multirotor, it has to have two or more main rotors that provide lift, as opposed to, say, a fixed-winged aircraft such as an airplane. And to distinguish between the various types of multirotors design, we use the number of rotors they have as a guide. Moving forward, for the sake of keeping things simple, I will refer to multirotors as drones, and we'll use the term motors instead of rotors. So, let's have a look at how a drone works at the most basic level, and we'll use a quadcopter as an example. A quadcopter design has 4 motors. It is one of the many drone configurations out there, and it has a lot in common with one of the most iconic flying machines, the helicopter. However, unlike the helicopter, the quadcopter uses 4 motors, 2 are spinning clockwise and the other 2 are spinning counterclockwise to provide balance. Motion is achieved by changing the speed of the motors, and everything is controlled by a tiny onboard computer called a flight controller. It tells the motors how fast to spin depending on the input from the onboard sensors and the pilot. So let's have a quick overview at a few drone configurations, starting with the quadcopter as just discussed. The quadcopter has 4 motors mounted on a symmetrical frame with 4 arms. The arrow indicates which direction the aircraft flies when going forward. You can build quadcopters in different designs as well, but the most common one is the X-shaped design. This is because the X style provides the best flight characteristics. You have access to a more stable thrust and maneuverability since you have 2 motors at the back, and in case you want to mount a camera on board, an unobstructed view. Next up, if we take away one motor, we have the tricopter. It works by using 3 main motors set up in a cool Y-shaped design. All the motors usually spin the same direction. The arrow indicates which direction the aircraft flies when moving forward. The tail also uses an additional servo motor in order to manipulate the direction the aircraft flies. This configuration is slightly cheaper to build since you are only using 3 main motors and all the propellers are the same shape. Another advantage of this design is that it produces an aircraft with incredible agility and very fun flight characteristics. On the flip side, however, this design offers less stability than other configurations, and the mechanism required for the tail is not as robust during crashes. Additionally, as you can imagine, this design would come with less lifting power as well. Next, we have the hexacopter. It flies with the help of 6 motors on a symmetrical frame. It's very similar to quadcopters in terms of flight mechanics. In this instance, there are 3 motors that spin clockwise, while the other 3 spin counterclockwise. The arrow indicates which direction the aircraft flies when moving forward. Having more motors means the aircraft can carry heavier things, and if during flight one of the motors fails, it can still land safely. The downside to this design, however, is that it uses more motors and needs more battery power, so it's slightly more expensive to build. Finally, let's have a look at the octocopter. It flies with the help of 8 motors on a symmetrical frame. The flight mechanics are still pretty much the same as the quadcopter. In this instance, 4 motors are spinning clockwise, while 4 are spinning counterclockwise to provide balance. The arrow indicates which direction the aircraft flies when moving forward. You can almost see this as an upgrade to the hexacopter in terms of lift capacity, and it can land safely even if 2 motors fail during flight. The downside of this configuration, of course, is that 8 motors will need a lot of power, so you will need to have multiple high-powered battery packs, which can get a bit expensive. One of the main uses for this type of drone is to pair it up with professional video equipment that would otherwise be too heavy to carry for other type of drones. Amazing! This concludes our quick intro into how a drone works and some of the popular designs out there. Next, you can check out the Jargon Buster and the tools requirements before heading over to section 3, where we will finally start putting together the drone. Hi everyone, and welcome to the first build log. This video won't be about the frame used in this course since it doesn't require much assembly. I figured it would be a good idea to include in an alternative frame build so you could see how other frames are put together. For this build, we will need a T8 screwdriver for the screws and some small pliers to secure the nuts. The frame we're looking at consists of 3 plates that fit together to form the base and 4 individual arms that are mounted with nuts and screws. So, let's begin and see how it goes. The middle plate of this frame is actually an integrated power distribution board, which we will talk about later. It comes with various solder pads which allow us to connect all of our components directly onto the board. Here you can see that most of these solder pads are outputting the voltage of the connected battery. And in the middle of the plate you'll notice that there is also a small step-down voltage converter which outputs at 5 volts. The base consists of 2 plates for the bottom layer, which sandwich together to hold the arms in place. And the first step is mounting the aluminium spacers onto the middle layer of the base. It is a good idea to use these red spacers that are designed to prevent shorting the power distribution board we're screwing into. Next, flip over the middle layer and it's time to mount the arms. It's best to do 1 screw at a time and do not fully tighten the screws until all the arms are in place. Once all the arms are secured and nothing is out of place, go ahead and fully tighten all the screws and nuts. Once the camera plate is in place, proceed with mounting the top plate. One thing you might find is that sometimes cheaply manufactured frames have holes that are slightly misaligned. This is entirely okay and nothing to worry about. Just adjust the holes slightly with a small tool like a flathead screwdriver until everything fits. Amazing! This concludes the first build log. Join me in the next lesson where we will talk about motors. Okay, so drones use brushless DC motors, which differ quite a bit in design compared to their brushed counterparts. The motors are based on a cylindrical shell with magnets called the rotor, which rotates around a core of tightly coiled wires called the stator. The two main non-technical differences that are relevant to us are, unlike brushed DC motors where there's a small shaft that rotates, it's the entire outer shell of the brushless motor that spins, and the propeller is mounted onto the top of the rotor itself. Another difference is that brushless motors aren't driven by a direct power input with two wires. As you can see from the stator example, besides the two power wires, there's also a third, which is the signal wire. And the whole thing is controlled by a speed controller, which we will discuss in a later lesson. Now, one of the main reasons drones use brushless motors is that they offer longer lifespans under intensive use. They also produce minimal friction while producing a lot of power in a relatively small package, which, as you can imagine, makes them ideal for this hobby. One disadvantage, however, of brushless motors is that they are slightly more complex to run and require a separate controller and software, which is the speed controller. Motor design is obviously quite complex, but thankfully there isn't much we need to know in detail about the workings of these motors in order to use them. And to keep things simple, I'll show you the main few things that we need to consider when buying these motors. Let's dive right into it, and the first thing we will look into is the kV rating of the motor. The kV notation represents the number of revolutions a motor turns when 1 volt is applied to it. Arguably, the kV rating is the most important when selecting a motor, since it will be directly related to the type of drone you're building. Essentially, different sized drones require different kV capable motors. So, for example, bigger drones carrying video equipment require a lot of lifting power. This is where motors with low kV ratings are very useful. These motors will produce more power behind every rotation without using excessive current, and the result is that they can drive bigger, more efficient propellers all while spinning much slower. And on the flip side, for fast, racing type drones, motors with high kV rating are better suited. These motors will have less power behind every rotation, but they will have a much higher spin rate, and because they spin so fast, they can better make use of smaller, less efficient propellers, allowing your build to have high maneuverability and speed. But what exactly is the kV rating and why does it actually matter? One way to simplify this is to think of the kV rating of your motors as the ideal spin rate. The motors will always try to do their very best to get as close as possible to their kV rating. To put things into perspective, let's imagine you have a high kV rated motor which spins really fast. It has a relatively small propeller attached to it, which is a great combination for small and agile drones. Now imagine the same motor but attach a much bigger propeller to it. The motor doesn't have a lot of power behind each rotation. It will struggle to reach the ideal spin rate and draw a lot more current than usual. And after struggling for a bit, it might eventually burn out. Whereas the opposite is also true. Take a motor with low kV rating, it produces a lot of power behind each rotation. Now mount a small propeller to it. The motor will spin very close to its ideal spin rate since there is not much resistance. Most of the power will be wasted and not a lot of thrust will be produced, which of course isn't ideal either. Okay, so in an attempt to simplify and answer the question, which motor do I actually need? Just remember that bigger motors with low kV rating, capable of producing a lot of power, will be better matched with bigger propellers. They will be ideal for bigger sized drones that require a lot of lifting power, where slow movements and stability is the goal. And on the other hand, smaller motors with a high kV rating will be matched up with smaller, less efficient propellers, making them ideal for smaller racing type drones, where fast movements and agility is the goal. Okay, so let's have a look at the motor that we are using in the build for the course, and analyze what the specifications tell us. The first number, BR2205, in the name means different things depending on the manufacturer. Sometimes it describes the diameter and length of the motor's internals, and sometimes simply is a model number. The next three things in the spec sheet are more important and will help us pair up the motor with the appropriate speed controller and battery type. This motor is designed for fast and agile drones since it has a pretty high kV rating at 2600 kV. It actually supports 3 different types of battery packs, and there are 2 different values for the current draw depending on which type of battery is used. I'll explain speed controllers and battery system in detail in later lessons. So, to summarize, first step is to decide which type of drone you would like to build. Second step is to choose a frame like we discussed in a previous lesson. After that, there are three main things to keep in mind. First of all, the kV rating, which will depend on the type of drone you want. Next up is the max current draw in amps, to help you choose your speed controllers. Finally, the type of battery it supports, to help you choose a battery as well. Fantastic! That concludes the lesson about motors. Join me in the next lesson, which is a build log, where we will mount the motors to our frame. Hi everyone, and welcome to the build video where we shall mount the motors to the frame. Since I had not used these motors before, I'm first testing how everything fits together before screwing anything in place. As seen from this example of an older drone build, some frames comes with these little round motor mounts that allow you to attach a wide range of motors to the frame. However, we don't need motor mounts to the specific frame we're using in this build, since the motors can be attached directly to the frame. The 4 motors for your drone come in sets of 2. One pair will spin clockwise while sitting opposite to each other, and the other 2 will spin counterclockwise and also sit opposite of each other. The specific motors we are using in this build come with a very handy way of indicating which direction they spin. The tops of the motors are marked black or white, which makes it very easy to identify them. One thing to keep in mind is to mount the motors with the wires facing towards the middle of the frame. This will make attaching the speed controllers nice and straightforward. Let's dive right in and attach the first motor to the frame. There are 4 hex screws per motor. After the first one has been mounted, I proceed with mounting the remaining 3 motors onto the frame and complete the motor mounting part of the build. Amazing! This concludes the motors build log. Join me in the next lesson where we will explore the electronic speed controllers. The next 2 lessons are about the power systems, and we start with the electronic speed controllers, or as they are often called, ESCs. Just like the motors, bunch of scientific mumbo jumbo goes into designing speed controllers. Thankfully, we don't need to know any of that either. You can think of speed controllers as the bridges that link up several components. They link up the motors, the battery, and the flight controller. They are used in practically all radio-controlled hobbies where there's a need to control a motor. Simply put, the main purpose of the speed controller is exactly what the name describes: assist the flight controller in controlling the motors. They do this by taking control signals from the flight controller and translating that into pulsating electrical power to the motors. Depending on what the flight controller wants the motor to do, the speed controller will adjust power going to the motor accordingly. Okay, so now that we know what speed controllers are for, what do we need to consider when buying some for your drone build? When looking for speed controllers, main thing to focus on is the amp rating. As you might remember from the previous lesson, the motors will draw a certain amount of power, which is also rated in amps. It is crucial that the amp rating of your ESC is higher than the max current draw in amps the motor will use. As an example, let's re-examine the motor we discussed in the previous lesson. The maximum current draw for this motor when using a 4S battery pack is rated at 27.6 amps. So when choosing a speed controller to accompany this motor, we must make sure that the amp rating is higher than the motor's. In this case, 27.6 amps. A speed controller's amp rating doesn't need to exactly match the motor's, it just needs to be higher than what the motor can use. For example, a motor that draws 10 amps will happily work together with an ESC that has an amp rating of 12 amps. Additionally, ESCs will be listed with a secondary higher amp rating as well. This number describes a burst current rating, and it is a protective feature in case of a surge in power draw by the motors. On the flip side, it's pointless buying speed controllers that have a much higher amp rating than the motor needs. They might be more expensive or be physically bigger and heavier. Another thing to be aware of is the software that runs the speed controllers. It might not seem like it, but a speed controller is in fact a little computer that handles all the commands received from the flight controller. And depending on the software in charge, it can affect the performance quite a bit. Which brings us to BLHeli. Currently, this software can be found in a wide range of speed controllers. BLHeli brought many improvements and has simplified handling the speed controllers quite a bit. The software supports a pretty sweet graphical interface that allows you to set up and apply updates easily. Previously, in order to apply any kind of updates to your speed controllers, you would need special programming hardware. Whereas now, for most of the speed controllers that support BLHeli, you can apply updates directly through the flight controller. There are also plenty of options available to fine-tune things in case you want to take things to the next level. Finally, one last thing we need to keep in mind when buying a speed controller is the protocol that it uses. Simply put, ESC protocols describe the way the speed controllers talk to the flight controller in order to get instructions about motor speed. Currently, there are two families of ESC protocols. They are the analogs and the digitals. And the simplest difference between all the various protocols is the speed of communication. As a beginner, you'll spend majority of the time practicing flying and fine-tuning things, so a specific protocol doesn't really matter much. However, for the sake of future-proofing your builds, let's do a brief overview about some of the protocols out there. Let's start with the analog family of ESCs. The oldest of the analog protocols is PWM. It is used in many electronic applications. The PWM protocol was a bit slow and improvements were needed. And to remedy the delays and increase the speed of communication, a faster protocol was developed called the One-Shot 125. This system uses shorter pulses and is around 8 times faster than PWM. The next update brings more improvements, called the One-Shot 42. It uses even shorter pulses and is around 24 times faster than PWM. Lastly, there is the Multi-Shot protocol. It is the fastest of all the analog systems currently, and it is a whopping 80 times faster than the standard PWM. It allows your drones to be incredibly responsive and agile. Right, let's have a look at the digital family of ESCs. Most of the digital ESCs that are available at the moment are all variations of the D-Shot protocol, and currently there are 3 stable versions of it, each consecutive one bringing a higher operating speed. We have the D-Shot 150, D-Shot 300, and the D-Shot 600. The numbers simply indicate the speed in terms of how much data is transmitted per second. So, D-Shot 300 is 2 times faster than D-Shot 150, and D-Shot 600 is yet again 2 times faster than D-Shot 300. The main advantage of digital shot is not necessarily the speed of communication, but rather the high accuracy since it's not influenced by electrical noise. It is also safer to use since it has error correction built in. D-Shot also makes using ESCs a lot easier. The analog systems needed calibration of all the internal clocks on the speed controllers to the internal clocks of the flight controller, or else the drone just wouldn't fly right. D-Shot eliminates the need to do that. In this course, we are building a quadcopter, which has 4 motors, and each motor will have its own speed controller. Okay, so let's examine the speed controller that we'll be using in this course. As we can see from the specifications, the first number on the table is also the most important one. This ESC can provide a continuous power output of 30 amps. You might recall the motor that we're using in this course carries a maximum current draw of 27.6 amps. The second number in the specifications shows us that this ESC can also handle a brief burst of 35 amps, which is a pretty useful protective feature in case of a surge in power draw by the motors. I chose this ESC for this build because it can provide the right amps for the motors, and it is also really small and lightweight. Okay, so to summarize, match up your speed controller amp rating with the amp rating of your motor. Aim for slightly higher amp rating than the motor will use. I will suggest that you choose a digital ESC since they are easy to use, have high accuracy, and have error correction built in. Right, this concludes the lesson about speed controllers and what to look for when buying them. Now that the theory is out of the way, join me in the next lesson, which will be a build log, where we will mount the speed controllers to the frame and connect them up to the motors. Hi and welcome to the build video where we shall mount the speed controllers to the frame and solder the motors to them. The solder pads on this side are where the 3 wires from the motors will be soldered to. These red and black wires are what will provide the power input, and the pair of twisted black and white wires will connect to the speed controller interface. As you can see, the underside of the speed controller is covered in a layer of plastic, so it's well protected. However, just as a precaution, I always apply a little extra layer of electrical tape onto the frame itself where the speed controllers will be mounted. This does 2 things. Provide protection in case the plastic casing wears out since the frame is made from carbon fiber, which is highly conductive. And it also provides a bit of a grip, so the speed controllers can't move around during flight. In the motor build video, I talked about mounting the motors with the wires facing towards the middle of the frame. Now we can see how that makes mounting the speed controllers nice and straightforward. The reason we mount the speed controllers at the end of the frame is that it allows the speed controllers to be cooled during flight by the propellers that will be rotating right above it. Speed controllers handle a lot of current, so can sometimes get a bit hot. Once we're happy with the placement of the speed controller, we'll lock it down with a cable tie. However, do make sure that you don't fully tighten the cable ties just yet. To keep things nice and tidy, we can also trim the motor wires as well. While doing this, always make sure that you don't trim the wires to the exact length you need. Instead, leave a little bit extra just in case. So, before we start soldering anything, let's go around the frame and mount the other speed controllers as well, while trimming the motor's wires a bit. Okay, it's time to heat up the old soldering iron and let's get started. First step is to apply a bit of solder to the wires. Then repeat the process for the solder pads as well. What we're aiming for is a nice smooth solder surface on the pads. You can use some tweezers to hold the wires in place while soldering them. As you might remember from the theory bit about the motors, 2 of them will spin clockwise, while the other 2 will spin counterclockwise to keep the drone balanced. And if you can remember, the motors we are using in this course have a very handy way of indicating which direction they spin. In this case, the ones with the black top spin clockwise and the ones with the white top spin counterclockwise. So, the 3 wires coming from the motors will have to be swapped around for 2 of the motors to make sure that they spin the opposite direction, in this case the ones with the white top. The wires coming from the black top motors are getting soldered straight to the ESC solder pads as they come from the motors. The wires coming from the white top motors will have 2 out of the 3 wires swapped around. So, in this case, I'm soldering the first wire from the right to the first solder pad on the right. Next, I have grabbed the middle wire and soldered it to the left pad instead. And then finally, solder the wire from the far left to the middle pad instead. Time to do the same to the other motor. Sometimes, after you have completed the drone build and are testing the system, you will find that the motors don't all spin the correct direction, in which case you will have to desolder some of these connections and swap the wires around. After we're done with the soldering of the motors, it's time to fully tighten the cable ties and trim the axis. Make sure that the cable tie is as central as possible. Here is the final result, and you can see the swapped motor wires as well. This concludes the speed controller build log. Join me in the next lesson where we'll explore the batteries and power distribution. Drone batteries require you to do a balancing act between weight and power. In an ideal world, we will have a battery that allows you to fly for hours. However, this is not the case. And generally speaking, the more capacity a battery carries, the heavier and bigger it becomes. So, in other words, there is a certain point where a certain battery is simply too large for a certain drone. Currently, the industry standard for drones are lithium-ion polymer batteries, LiPo for short. LiPo batteries can be smaller and lighter while still carrying a lot of power compared to other battery technologies, which, as you can imagine, makes them ideal for this hobby. When choosing the battery for your drone, there are a few things to consider. First, let's talk about the battery voltage. Drone battery packs usually consist of a few individual LiPo cells packed together, and a single LiPo battery cell carries around 3.7 volts. Some toy drones out there use a battery with a single LiPo cell. So, logically, a 2-cell battery pack would then carry 7.4 volts, and a 3-cell battery pack should carry around 11.1. The number of cells a battery pack has is indicated by a number and then followed by the letter S. The type of battery you can choose will depend on the type of drone you want to build, the motor you have chosen, and the speed controllers to accompany them. The next thing we need to think about is the capacity of the battery. Battery capacity is measured in milliamp hours, which basically means how long the battery will last and how much flight time it can give. So let's say you have chosen the frame, the motors, and the speed controllers. From the specifications of the motors and the speed controllers, you have noted that they both can support up to a 4S battery pack, which is a battery containing 4 LiPo cells. Now, depending on the size of the drone you're building, you would choose the capacity of your battery accordingly. Do keep in mind that an increase in capacity usually increases the size and the weight of the battery. Finally, the last thing to consider when purchasing your battery pack is the C rating. The C rating tells you the discharge rate of the battery. For example, the battery pack we'll be using for this course has a capacity of 1300 mAh and a C rating of 70C. It will be a 4S battery pack. The C rating tells us that this battery can be discharged at a rate of 70 times its capacity. So in this case, 1300 mAh times 70, which equals 91,000 milliamps, or in other words, a maximum of 91 amps. Now, the reason we need to understand C rating is that just like when choosing a speed controller that had to be rated at a higher amp rating than what your motors can use, your battery also needs a discharge rate that's higher than the combined current draw of all your motors. Most drone batteries that are sold these days will come with an acceptable C rating, so it's not really something you need to worry about, but it's good to be mindful about it. Before we look at the battery we're using in this course, one thing I would like to remind everyone is battery safety, as highlighted in the safety document. Battery safety is a very serious subject in this hobby. The LiPo technology provides amazing performance, however it can be quite volatile and requires to be treated safely. Okay, so let's have a look at the battery used in this course. It's an Infinity 4S graphene LiPo battery pack. From the specifications, we can see that it has a capacity of 1300 milliamps. It's a 4-cell battery pack that produces 14.8 volts. It has a C rating of 70C, which means it can generate around 91 amps in total. And it only weighs around 150 grams, which is useful since we're building a rather small 210mm sized drone. Now that we understand a bit more about batteries, let's talk about ways of getting that power to all the systems. Power distribution. There are 2 ways you can distribute power on your drone: by directly wiring up all the components to the battery pack by either using bullet connectors or just soldering wires, or by using something called a power distribution board. Before I explain both options, let's recap the components that we need to provide power to. First, we have the speed controllers. These can be usually wired directly to the battery, provided the voltage input-output is matched up. For example, the speed controller we're using in this course can support up to a 4S battery pack that outputs 14.8 volts, and the battery we're using also outputs at 14.8 volts. Motors are connected directly to the speed controllers, and they also need to have the correct input voltage. One extremely important thing to remember is that not all the components in your build will run off the same voltage. So, for example, the flight controller, the radio receiver, and some cameras run on a much lower voltage, which is usually around 5 volts, and they should never be connected directly to the battery. Certain speed controllers out there do come with a step-down voltage converter built in, called a battery elimination circuit. This allows you to power lower voltage components directly from the speed controllers. But if your speed controller doesn't have a battery elimination circuit, you will need a separate voltage converter to power the lower voltage components. Okay, so let's have a look at distributing that power. One way to distribute power is by using a breakout cable. The great thing about these cables is that they have bullet connectors that allow you to quickly assemble or disassemble things. You can solder bullet connectors throughout the entire system to make everything really modular. Another way is by using a dedicated power distribution board. The power distribution board, or PDB, has solder pads for all the components. Quite often, they also include voltage converters that output 5 volts for all your lower voltage components. Since the PDB allows you to connect everything directly onto the board itself, it makes the overall build look clean and organized. Is one way better than the other? I think both options work equally well, especially if your speed controller has a 5-volt converter built in. However, I personally prefer the power distribution boards since everything is hardwired, there's less chance of failure by things coming apart, and it produces a cleaner build with less wires and less mess. So, to summarize, there is a direct relationship between battery capacity, size, and weight. Weight is an important factor since it can influence flight time and performance. So, when purchasing the battery, look at voltage, power, C rating, and weight. To distribute power, you can either use a power distribution board or simply connect everything together using a breakout cable and bullet connectors. If you do decide to go for a PDB, find one that has a 5-volt converter built in to power those lower voltage components. Finally, LiPo batteries can be temperamental and are extremely flammable if not looked after. This concludes the lesson about batteries and power distribution. Join me in the next lesson where we will wire everything together and see the power distribution board in action. Hi and welcome to the build video where we shall mount the power distribution board to the frame and solder all the speed controllers to it. The first thing I'm soldering to the PDB is the main plug that connects the battery to the system. It's called an XT60 plug. To make the soldering job easier, I'm attaching the PDB to a helping hand. I also found that the lid of a screwdriver set was the perfect height to help support the XT60 plug while soldering. Since this is going to be the major point of contact for the battery and all the current flowing through the system, we have to make sure that the connection is nice and strong. What we're looking for is a nice smooth surface like this, so make sure that your soldering iron is nice and hot before starting. The frame has these 4 holes where you can mount all the important components such as the power distribution board or the flight controller. To make sure that the PDB won't short out, instead of using metal spacers, I'm using nylon ones. They are pretty strong and you don't have to worry about them breaking. I will include a link to where to buy them in the parts list. Do make sure that everything is nice and tight before proceeding. This frame comes with a battery strap that is pushed through the middle. So before we mount the power distribution board, let's push the battery strap through first or else we'll have to take it all apart again. Now, to mount the PDB onto the frame, I use the same spacers as the one below the board itself. The idea is that the flight controller will be mounted on top of the power distribution board. This is something called a stack, and I will talk more about this in a later lesson. With the PDB mounted, it's time to solder the speed controllers. Always make sure that everything fits together before you start trimming the wires, and it's best practice to always leave a little bit extra wire when trimming, just in case. Before I solder the wires onto the PDB, I'm applying a bit of solder onto the ends of the wires and the pads themselves. This makes the soldering process a lot easier. You will notice that the PDB has multiple solder pads. How do you know which ones are the right ones? It's actually really easy to identify since everything is marked as positive and negative terminals. This PDB has 6 spots where you could solder speed controllers, even though we only need 4. The reason for that is that it could also be used when building a hexacopter which uses 6 motors and speed controllers. Alternatively, you could also use the additional solder pads to power other high voltage components like some cameras. Okay, so let's start soldering the speed controllers. Just as before, I'm using a tweezer to help me steady the wires. Amazing! All the speed controllers are now soldered onto the board. There is still some more to solder onto the PDB and it will be used again later when we mount the flight controller onto the frame. That's all for this build video. Join me in the next lesson where we'll talk about the flight controllers. Usually, you just connect the radio receiver up to the speed controller, which in turn controls the motors. Things get a bit more complicated with multicopters, and we must put tiny cute computers in charge. This lesson will explore why we need flight controllers, and we'll also talk about what to look for when buying them for your own super awesome drone. We will then look at a specific flight controller that we'll be using for the build in this course, and finally we'll have a quick look at an optional flight controller board that makes building drones even easier. Flight controllers come in different shapes, sizes, and features, and the basic flight controller has the following things: a processing unit to calculate all the variables of flight, sensors to keep things flying smoothly, an interface to connect radio control hardware like a radio receiver, an interface to connect motor control hardware like speed controllers, and optional interface to connect additional sensors and devices. Okay, so what is the purpose of a flight controller and why do we need one? The flight controller, often shortened to just FC, is essentially the brain of your drone. The simplest function of the flight controller is to take pilot commands and translate them into motor movements. It is essentially a mini computer that has a variety of sensors built in to assist the pilot during flight. Majority of the flight controllers for drones will come at least with 2 types of sensors built in that are necessary for a stable flight. You will have a gyroscope sensor which senses orientation, and an accelerometer sensor which senses acceleration. Essentially, they both detect motion and allows the flight controller to keep everything stable. In the world of radio-controlled hobby, it makes flying multicopters rather unique, since usually the person holding the control has direct control over the motors. For example, the engine of an RC boat or the engine of an RC plane. Any input on the transmitter is directly translated onto the motors. In a multicopter, however, it would be very difficult to precisely control multiple motors directly from the transmitter and balance the craft. This makes flight controllers rather useful since they make flying multicopters almost pain-free. A flight controller will take care of the following things: take commands coming from the transmitter directed by the pilot, keep the drone balanced by taking measurements from the available sensors to counter any external influences like wind, allowing precise control of individual motors to make the drone move around and perform actions. Some more advanced flight controllers can also support additional sensors for features such as altitude hold, GPS control, auto navigation, and more. They can also allow control of external devices such as camera gimbals and actuators. Flight controllers are crucial for a drone to work, and as you might already know, there is an abundance of choice when it comes to parts for this hobby. That includes the flight controllers. They can range from relatively cheap to kind of expensive. Now at this point you might be wondering about the question: which is the best flight controller out there? The answer is that one flight controller might be better than another, however there is no such thing as the best flight controller. The reason for that is there are specific boards available for specific applications, and essentially it all comes down to what you want the flight controller to do. In other words, what type of drone are you building? For example, a super fancy flight controller with a high price tag might come with advanced features such as GPS control with return to home, altitude hold, or support advanced software for mission planning and battery management. These types of flight controllers might be better suited for drones carrying expensive video equipment, but let's say you're building a fast little drone called Sir Crash-A-Lot, which would benefit from a cheaper flight controller since you wouldn't need advanced sensors on that, neither would you need any GPS control. Simply put, certain flight controllers might be overkill for certain type of drones. The radio control hobby is a field that evolves at a very fast pace, and because of that there are now several different generations of flight controllers available on the market. You might have already come across terms such as F1, F3, F4, even F7 attached to flight controller names. These terms simply are an indication of the processing hardware that lives on the flight controller. Generally speaking, the higher the F number, the faster the overall system operates. And another generalization is that quite often the higher the F number, the more connection ports there are for additional devices to be connected to the flight controller. Things such as your GPS sensors, telemetry sensors, and on-screen display sensors all use ports on the flight controller. Essentially, the more ports there are, the more you're able to expand the functionality of your drone. One thing you should consider before buying anything is that do we really need a super fast processing chip on board with lots of crazy ports considering we're only building a racing drone? Be assured that for a first time build, any generation of flight controller will do the job perfectly fine. In fact, there are still many F1 flight controllers out there and they work really well. Said that, if the budget allows, go for an F3 generation of flight controller just to balance price versus functionality. Okay, so the firmware is a software that is in charge of the flight controller, and as you can imagine, it plays a pretty important role. Besides affecting flight performance, it will also dictate whether you have the flexibility to connect any external devices, such as camera gimbals, LED lights, or even external sensors. At the very basic level, the firmware should allow you to do the following things: set up and fine-tune flight characteristics of the drone, set up radio transmitter and receiver functions, calibrate any and all sensors, and set up flight modes. Thankfully, the variety of great firmwares available right now is far less than the variety of flight controllers that support them. And in this course, we'll be focusing on the Betaflight firmware, which we'll discuss later on. For this course, we'll be working with an F3 flight controller board. It comes with a gyro sensor and an accelerometer sensor. F3 flight controllers like these are usually based on a 32-bit processor running at 72 MHz. Combined with the onboard sensors, it will offer decent flight performance. The main advantages of this board that is cheap, but it still provides a wide range of connectivity choices to enhance the functionality of your drone. Yet, despite all the different ports, the entire board remains small and is extremely lightweight, making it ideal for small drones. The small size of the board allows it to be mounted in something called a stack, which is simply a few boards stacked up on top of each other. An example of a stack would be a flight controller board, a power distribution board providing power to all the systems, a video transmitter board in case you want to have a camera for FPV flight, and in some cases a 4-in-1 speed controller board providing power to motors instead of 4 individual speed controllers. Before we carry on to the next lesson and watch the build video for this flight controller, I want to briefly talk about another flight controller board that makes building drones even easier. Since the way we're building the drone in this course is quite modular, the opposite can also be true. Some flight controllers come with everything built into a small package, which is not a lot bigger than the usual flight controllers. They're called all-in-one boards with the following built in: a flight controller, of course, power distribution to connect speed controllers, sometimes a radio receiver for control, and sometimes even a video transmitter for a camera. Normally, every individual part takes up space and adds to the overall weight of the drone. With an all-in-one flight controller, you don't need to source individual parts. With everything built in, it often minimizes the weight of the entire build, while saving us time and money. And as a bonus, they allow you to build really clean-looking drones without any mess of wires. There is, of course, a downside to sacrificing modular design. In case any of the components on board break down and you don't know how to fix it, you'll have to replace the entire thing. Okay, so to summarize, when choosing a flight controller, first is to decide what kind of drone you want to build. Secondly, understand what type of flight abilities you need. What sort of sensors and assistive features do you want during flight? Would you want additional ports with the ability to expand the drone's functionality at a later time? To make things easier, keep in mind that pretty much all flight controllers will come with the ability of self-stabilization at minimum, allowing for a stable flight. Lastly, there's the matter of price. How much do you want to spend on the flight controller, keeping in mind the overall budget for the build? If this is your first build, there will be a bit of a learning curve and possible crashes. So, it might make sense to buy something cheap that can be replaced easily and often. Fantastic! This concludes the lesson about flight controllers. The next lesson will be a flight controller build log, where we will mount the flight controller to the frame and learn about soldering all the various interfaces. Hi and welcome to the build video, where we shall mount the flight controller to the frame and solder all the various interfaces to it. The flight controller is a crucial part of the drone, and it's important to get all the connections right. The first thing we need to do is to figure out some power going to the flight controller. Thankfully, the power board we're using comes with a dedicated solder pad for that. So the first step is to pre-tin the flight controller's connector, so it will be easy to solder onto the power board. Here you can see that I'm using some helping hands to secure the wire so it's easier to solder. These are the solder pads we'll be using to power the flight controller. Make sure you use the 5V ones and not the 12V ones, or else your flight controller might release the magic smoke. Most flight controllers will have an indication of how to orient the board on the frame. In this case, there's a small arrow that indicates forward direction. Double check the wire length to make sure it will reach after it's soldered. Next, I pre-tin the solder pads as well. You can always directly solder wires to pads, however I find that pre-tinning makes soldering a little bit easier. Once that's done, go ahead and solder the flight controller power connector onto the power board. This specific flight controller comes with a handy way to monitor battery voltage. This is done by a small connector that links the flight controller and the power board. Here we can see the flight controller side of where the connector will plug into. So the first step is to see how long the wire needs to be and trim the excess. After that, just like with the power connector, I'm pre-tinning this connector as well as the solder pads on the power board. For now, leave the connector unplugged and let's move on to the next thing. Next up, we will solder the speed controller interface onto the flight controller board. Before we start soldering these, remember to make sure that all the pins are fully inserted into the board and you're happy with how it looks, since it will be a pain to desolder them. Here I am double checking whether everything fits well together. I also noticed that if I solder the pins as normal, it will make all the wires stick out from the side of the frame and things will look rather messy. To prevent that, what I'm going to do is flip the orientation of the pins so they face inwards towards the middle of the frame. This will work perfectly fine, however we need to remember two things. Firstly, we have to make sure not to fully insert the pins into the solder pads and to leave a bit of space. Otherwise, we won't be able to insert the speed controller connectors into them since they will be too close to the board itself. Secondly, to make sure to flip the speed controller connectors upside down to accommodate the flip of the pins. Here, I'm using some spare connectors to help me figure out how far down I can push the pins into the board. Once I'm happy with how the pins and the connectors look, it's soldering time. I'm leaving the connectors plugged in for the time being to make sure nothing moves while I solder things into place. Now take your time with this and do it slowly, one by one. Do make sure that none of the pins end up soldered together. Here we can see the finished solder job. I can now go ahead and remove all the connectors. If you look closely, you can notice that there is some space underneath the pins. Next, we're going to be soldering a couple of pins right next to the speed control interface. For certain boards, in order to transfer software onto them, you need to short a couple of pins to enter something called bootloader mode. Bootloader mode is simply a special state that your flight controller goes into so it can accept new software. It also works as a failsafe in case something goes wrong with the software and you need to erase everything and start again. Here I'm soldering the pins to the board and that's all the soldering jobs done. Now go ahead and secure the flight controller onto the frame with some screws. Finally, the last thing remaining is to attach all the various connectors onto the board. First thing we're plugging in is the battery voltage monitor, after which I tuck away all the excess wire underneath. Next up is the power connector that will provide 5V power to the flight controller. The flight controller takes power input from the same interface the speed controllers will connect to, so go ahead and plug in the connector into one of the spare speed controller ports. It's really important to make sure that you get the polarity correct. Keep in mind the plus and minus voltage pins. Next, we'll plug in the speed controller connector, but remember that we flipped the orientation of the pins, so keep an eye on the orientation of the connector. Normally, the signal wire would be the top pin, but in this case, the signal wire is now at the bottom. So, make sure that you flip the speed controller connector to reflect that. Before I plug the connectors in, I'm marking them with which speed controllers they belong to. After they're all connected, I tuck away the excess wire underneath. That is all for this build log. Join me in the next lesson where we will talk about the control in radio control. Have come a long way, and these days we're spoiled with some really helpful features. We now have access to radio systems with nice big displays, the ability to save settings for multiple models without making any hardware changes, two-way communications from the transmitter to the receiver, and even the ability to update the software running on the transmitter itself. Let's dive right in and start with the basics. The radio systems for your drone comes in two parts. We have the transmitter and the radio receiver. The transmitter is how you control the drone remotely, and the radio receiver lives on the drone itself to relay pilot commands to the flight controller. In this lesson, we'll talk about a variety of concepts that will help you choose the radio system you need. We'll have a look into radio channels, transmitter modes, radio frequency, and also the communication protocols. Out of the four, the two important ones are the channels and the communication protocols, since they directly influence what the system can do. Additionally, we'll also talk about price ranges. And lastly, we'll have a look at a radio system that we'll be using in this course, which is a great starting point for beginners. Right, time to demystify all this crazy jargon. Let's start with channels. Simply put, the number of channels your radio system supports directly translate to how many individual actions you can perform on your drone. For example, to successfully fly the type of drone we're building in this course, a quadcopter, you need to be able to control 4 individual actions. Let's find out what they are. First thing that we will need to control is the throttle, or the speed of the motors. The further you push the stick, the faster they will spin. Secondly, you need to be able to control the horizontal direction of travel. In other words, to be able to turn the drone left and right, which is called the yaw. Next, you need to be able to tilt the drone forward and backwards, kind of like what a plane does, which is called the pitch. And lastly, you need to be able to roll the body of the drone left and right, also pretty much exactly what a plane does when it's turning. So 4 channels are the bare minimum to control the drone we are building. Being able to control the drone with the 4 channels is a lot of fun. However, having 5 or more channels is a bit more useful. Depending on the flight controller, the extra channels, called the aux channels, can be assigned switches and dials on the transmitter. This allows us to expand the functionality of the drone. Things such as multiple flight modes that change flight characteristics, altitude hold allowing a stable hover, adding additional sensors and LED lights. Essentially, all of these extra features require a dedicated channel so we can activate and deactivate them when needed. Okay, so now that we know what channels are for, let's talk about modes. The mode of your radio system is relatively easy to understand, and there are 2 modes majority of the systems fall into, Mode 1 and 2. Now, the main difference between the 2 modes is that they have different positions for the control sticks. Mode 1 has a throttle and yaw control on the right side of the transmitter, whereas Mode 2 has a throttle and yaw control on the left side of the transmitter. Now you may ask yourself, why is there a difference? It simply comes down to personal choice. And to figure out which mode feels best for you, get yourself a toy drone that allows you to flip the modes around on the controller. Toy drones fly the same way as the ones we're building in this course, but of course cost a lot less, making them ideal to practice on. Next, let's have a look at the frequency of your radio system. It is the wireless signal that your radio system uses to communicate between the transmitter and the radio receiver. These days, many hobby-grade radio systems on the market operate on the 2.4 GHz frequency, and it has revolutionized the RC world. It's highly versatile against interference, which means multiple people can use the system together in close proximity without being worried about conflict. It does this by using a feature called frequency hopping, where the transmitter constantly scans for the best possible connection to the receiver. This makes the system incredibly reliable, and the possibility of the user losing connection to the aircraft while within range is minimized. Now, before the 2.4 GHz system came along, there was another system that dominated the airways, the 72 MHz frequency, which now is pretty much phased out when it comes to drones. One of the great things about this frequency was that it allowed a much longer range of control. The downside, however, was that it didn't handle interference very well. There would often be conflict with other people using the same frequency nearby. Additionally, the controllers that used this frequency had to be much bulkier, since that system required bigger antennas. Finally, another essential thing when buying a radio system is the communication protocol. In the lesson about speed controllers, we had a look at communication protocols, which were specific to how speed controllers work. Your radio system also needs a way to transfer information between the transmitter and the receiver. And communication protocols in this case describe the way the radio transmitter talks to the radio receiver, and vice versa in some cases. I won't go into how the various protocols work in detail, but will explain some of the more popular ones briefly, so that you know how to recognize them out in the wild when buying parts. Let's start with the basic one, which is PWM. It stands for Pulse Width Modulation and has been around for a very long time. It's also the one that is most widely supported by the majority of the flight controllers. It is an analog system where the length of a pulse when high represents specific values. It's also a pretty simple system, but the downside is that every channel requires an individual wire to carry the information, which, as you can imagine, can get quite messy if you have 6 or more channels. Next up, we have PPM, which stands for Pulse Position Modulation. It's also an analog system, but it takes the simplicity of PWM minus the complex wiring. The way PPM works is similar to PWM, but each signal is sent one after the other. This allows the system to work through a single wire and transmit all the channels, which is great news. This allows our drone builds to be much cleaner looking, and it takes away the possibility of us making mistakes wiring up individual channels. We will be using PPM for the build in this course since our radio receiver supports it and it's really easy to set up. Now that we know more about the 2 main analog communication protocols, let's have a quick look at some digital protocols as well. I'm talking about S-Bus and I-Bus. They both work pretty much the same way and are also both digital serial communication protocols. S-Bus was initially developed by a single manufacturer, however now many other brands use it as well. Whereas I-Bus, on the other hand, is a protocol specific to the FlySky brand. Digital systems do tend to be often superior to the analog counterparts by having lower latency and better protection against interference. And just as PPM, they only require a single wire to support multiple channels. Both of these protocols also support two-way communications between the transmitter and the receiver, which means that if your radio receiver supports it, you can have useful information like battery voltage levels going back to the transmitter. Sweet, now that we have talked about all the essentials, let's talk about price ranges. To choose a radio system, there are two routes you can take. Route 1, buy an inexpensive but good quality budget system to start with, and then upgrade later if needed. Route 2 is splash out and get the top of the range system from the start and future-proof your radio control adventures. In the world of radio control systems, you get exactly what you pay for. Cheaper systems can have lower build quality and have fewer features, and quite often the opposite is also true. The more you pay for a system, the better the build quality and more features there will be available to you. But as a beginner, do you really need something that will be able to do your dry cleaning and cook your dinner? If you choose the first option and go for a middle-of-the-range budget system, like the one we're using in this course, make sure you get one with at least 6 channels. This will ensure that you can cover the essential requirement of 4 channels to fly the drone and still have 2 aux channels to play with. Now, as promised, let's look at the radio system we are using in this course for the build. It's something we've already been looking at, the FlySky FS-i6. This radio system has been around for a while and provides amazing value. Despite the low price tag, it has an excellent set of features, making it ideal as a beginner's radio. You can usually buy the system as a transmitter and receiver package. However, for the build in this course, we'll be using an alternative FlySky radio receiver than the one it normally comes with. The reason for that being that this alternative receiver is a lot smaller and it also supports PPM, which means we can minimize the amount of wires on board as well. This radio system runs on the 2.4 GHz frequency and supports a nicely backlit LCD screen. The control sticks feel smooth and the overall build quality feels pretty decent. It comes with 6 channels, which is ideal for our beginner drone build. The first 4 channels will be used to control the drone, and then we have 2 aux channels that we can assign to whichever functionality we need. In this case, one of the aux channels we have available will be used to arm and disarm the drone. Most flight controller firmwares out there allow you to activate the motors on a drone by moving the sticks in a certain way. However, having a dedicated on and off switch that we can trigger from a safe distance is much better. The other aux channel will be used to toggle between flight modes. We will cover flight modes and other flight features in more details during later lesson. To summarize, when choosing a radio system for your drone, main things to look for are the number of channels the system supports and which communication protocol it uses. In the build for the course, we'll be using PPM protocol because of its simplicity in the wiring and setting up. There are 4 controllable actions for your drone when it's in the air: the pitch, the yaw, roll, and throttle, which is how fast the motors spin. You also need to decide if you want to start with a decent mid-range system and upgrade later, or start off with the high-end stuff and future-proof your build. Lastly, 2 types of transmitter setups that are most common: Mode 1 and Mode 2. Which is simply a matter of preference. Amazing! This concludes the lesson about radio systems. Now, join me in the next lesson, which is a build blog showing the installation of the radio receiver. Hi everyone, welcome to the build video where we shall mount the radio receiver onto the frame and connect it to the flight controller. However, before we dive in, we need to finish the frame first by building and attaching the top plate, which also contains a camera mount. So, let's begin. The top plate is attached by 4 metal spacers, so let's go ahead and screw those into the frame. Next, it is time to put the top plate together. It all fits together rather easily, and the camera mount can be used to hold a small FPV camera. Finish up the frame by screwing in the top plate and we are ready for the radio receiver. The radio receiver that will be used for this build is incredibly small, which is great for the size of drone we're building. It weighs just over a gram. You might remember from the previous lesson about radio systems where I talked about the various communication protocols, and this little radio receiver supports both iBus and PPM. In this case, we'll be using PPM since that's what the radio transmitter supports as well. Now, before we can use this radio receiver, we need to modify some wires. The flight controller we're using has its own specific port for the radio receiver interface, but it's not directly compatible with the connector that the radio receiver comes with. This is not really an issue, and we can easily modify both sides and make them compatible. First, we will modify the flight controller side. This connector is designed in a way that you could use a radio receiver that supports PWM, which, as you might remember, requires individual wires for individual channels. So here I am isolating the two power wires and the first channel wire. Next, I'm going to use a small hobby blade to lift the tabs on the connector so I can take out the extra wires since we won't be needing them. As you can see, it is pretty easily done. Here is the finished connector, and I'm just making sure that it still all fits. Time to modify the radio receiver side. The diagram on the radio receiver makes it really easy to identify which pins we need to use for PPM. It's always a good idea to do a quick test fit to understand how much wire you need to trim, and now we can go ahead and cut off the excess wires from the flight controller connector. Since I know for sure that this is where the radio receiver would sit, I'm going to go ahead and stick it down using some double-sided sticky foam. I'm also going to use a thin cable tie to tie down the antenna against one of the metal spacers on the frame. And this is how it all looks. Okay, time to carefully trim the wires from the radio receiver connector, making sure it will still fit. Once I'm happy with the length, time to snip away. Amazing! Time to join these two plugs together. First thing we need to do is remove an excess wire from the radio receiver connector. The white wire in this case is for the iBus communication protocol, and since we are not using it, it's safe to remove it. Next, I'm putting some thin heat shrink in place before I join up the wires. For the individual wires, I'm simply using some electrical tape to insulate them. Here is the finished connector all securely heat shrinked up. Now go ahead and plug both of the connectors back in, and we are done with this build log. Join me in the next lesson where we'll have a look at propellers. Such a huge variety of propellers out there. They can range in size, number of blades, the material they're made out of, and of course the price. In this lesson, we will unravel all the different specifications and measurements that are out there. So let's dive right in and find out what all the numbers mean. There are a few variations of how the manufacturers list their specifications, but the main concept is mostly along the following lines. It goes by propeller length times pitch angle times number of blades. To understand what this means, let's use a real-world example. Let's look at two propellers and figure out what the specifications mean. First up is the Gemfan 5030. The first bit is obviously quite easy. It tells us the name of the manufacturer, Gemfan in this case. According to the formula on the left, the second bit tells us that the propeller length is 5 inches and that it has a pitch angle of 30 degrees. Another way of listing the same propeller would be as 5 times 3. Quite often than not, you will find that there are 2 digits for the length of the propeller and 2 for the pitch angle. Okay, now let's have a look at another propeller of a similar size. Again, the first bit is easy, it's the name of the manufacturer. The propeller length in this case is still 5 inches, however, this one has a different pitch at 45 degrees. Finally, the number 3 at the end tells us how many blades this propeller has, and in this case it's a tri-blade propeller. Again, these propeller specifications could be written as 5 times 45 times 3. Now, the size of the propeller is an obvious measurement. The larger the number, the larger the propeller. But what on earth do we mean with pitch angle? Pitch can be defined as the distance a propeller travels during one full rotation. To put things into perspective, imagine the propeller on a boat. When the propeller rotates, the distance the propeller travels in the water for one full rotation is the pitch. So, is pitch really a crucial thing to look at when building a drone? Generally, the larger the surface area of a propeller, the more air it will push through, but it will also use more battery power at the same time. So, understanding pitch angles is kind of important to a certain degree. On the other hand, most propellers made for the type of drone we're building will definitely come with an acceptable pitch angle range. So, for your first few builds, you can experiment with various pitch angles and see what feels best for you when flying. Okay, so the next thing to remember is the propellers that are used on drones are designed in sets of 2. They come with similar but opposing shapes. So, in this case of the quadcopter that we're building, there will be 4 propellers in total. 2 of them are designed to spin clockwise, while the other 2 are designed to spin counterclockwise. So, when buying your propellers, make sure the pack contains both clockwise and counterclockwise propellers. Okay, so let's examine the propellers that we'll be using in this course and break down their specifications. The first bit tells us the brand name, and from the first number we can see that it's a 5-inch propeller. Second number tells us that it's a pitch angle of 40 degrees, and the last number tells us that it's a tri-blade propeller. These propellers come in a pack that contains 7 pairs of both clockwise and counterclockwise rotating propellers. An interesting thing about these propellers is that they're made from strong but flexible material that absorb force during impacts. This makes it rather difficult for them to break during crashes. To summarize, propellers can be made from several different types of materials. Generally, most manufacturers follow the following convention when listing specifications. It goes by propeller length, pitch angle, and the number of blades. Due to the size of the drone we're building in this course, the biggest propellers we can have are 5 inches. Fantastic, this concludes the quick intro to propellers. Join me in the next lesson, which will be a build log showing you how to mount the propellers onto the motors.